All right, guys, so let's get started. This is a very important chapter. Um, this will be a basis for a lot of stuff you do. It'll introduce many new things for you. Okay. This chapter is called this chapter is Oscillations, on oscillations. Oscillations is any motion that repeats itself. Okay, and we'll be considering one particular kind of motion that repeats itself, and it's called the simple harmonic oscillator. You've done a lab on this, so let me illustrate to you this motion. Okay. What happened? We don't want any damping. Okay. So we'll start off by considering a motion where there's no damping. There's zero damping. When there is no what does damping mean? What do you think damping means? Friction. So there's no friction, and so this motion will repeat itself forever. Okay. Now, for something to oscillate, what needs to happen is, okay, there are three kinds of energies here, but we'll start off by considering only two kinds of energies. Okay, so there's kinetic energy. There's gravitational potential energy because there's vertical motion. Okay, the gravitational potential energy is changing, and there's elastic potential energy. There's spring potential energy. And let me slow this down a little. Okay. Now, what do you see about the total energy? It's being constant through the entire motion. Okay. So for some system to oscillate, what needs to happen, you have to have two or three different kinds of energies or more, and energy is oscillating from one kind to another. Okay. And as long as there is no friction, energy is not being dissipated. Okay. If there is friction in the system, what happens is mechanical energy is turned into heat, and that gets dissipated, and the oscillation will die out. Okay. So this is the system we'll study. We'll actually start off with a simpler system. We will start off with a mass attached to a spring. Okay, and this will oscillate back and forth. Okay, so this is simpler because there's only two types of energy: spring potential energy and kinetic energy. Okay, and the system will oscillate, and energy will be transferred from potential energy to kinetic energy. Again, this will be on a frictionless surface. Okay, and this will oscillate back and forth. All right, so this is the system we are interested in studying. Our ultimate goal is to tell where the mass is at all times. Okay, so we want to know this function. Okay. Now the question is, how do you find that function? Okay, how do you solve for that? Okay, so this is a system. Okay. And we want to know the behavior of the system. Okay. Okay, so what governs the behavior of the system is the question. Okay. So, I'm sorry? Some kind of equation. And it turns out it'll be a differential equation. Okay, so that's why you study differential equations. So you'll be interested in studying various kinds of systems. This is the simplest system you'll start off with. Other more complicated systems you can think of. Okay, so here's another complicated system. Okay, here's tigers or lions, deer, grassland, and all that kind of stuff. Here is a more complicated system interacting with each other, and how do the population develop, okay, stuff like that. You can talk of the weather system, you know, and so on. Okay, so you will be interested in studying a system, the evolution of a system. The behavior of that system will be governed by some equation, and generally it's a differential equation. And then you'll solve this differential equation for that. Okay? So I'll give you the punchline. So the differential, the position of this mass is governed by, the behavior of this system is governed by this equation. Okay? So the position of this mass satisfies this differential equation. Okay? How do we get this differential equation? We'll see that in a second. Okay? So how do we come up with this mathematical model for the behavior of the system? I'll show you that to you in a second. Okay? And this is the simplest system we'll consider. Okay? So this chapter introduces differential equations to you, okay, the reason behind them, and we'll learn how to solve this differential equation. Okay, well, actually, I'll give you the solution to this differential equation. You'll study how to solve various techniques to solve differential equation in a math class. Okay, so you guys understand where we're going? We'll look at a system. We want to understand the behavior of the system. So, for instance, you want to know where the mass will be at all times. Okay, okay. All right, so oscillations is what we'll study. Here's the simple system we'll study. Okay, now, so here's a mass attached to a spring. This is the equilibrium position. Here's the equilibrium position. When you disturb the system from an equilibrium position, what happens is a restoring force comes into play. The forces that come into play want to restore the system back to its equilibrium position. You disturb it in this direction, it wants to restore it back there to the equilibrium position. Here's another example, a marble in a valley, you disturb it, and it wants to come back to its equilibrium position. Okay, you disturb it, it wants to come back to its equilibrium position. Can you think of a system where if you disturb it from its equilibrium position, the forces that come into play will not restore it to its equilibrium position?
If you're at the top of a hill.
Exactly. So here's an equilibrium position. You disturb it from an equilibrium position and it'll run away from it. Okay. So this is a non-restoring system. Okay. So this is a restoring system. Now this guy has a very special property. This force, the restoring force, is proportional to the displacement. Okay? And this system is easy to study. If the restoring force was like that, that's a much harder problem to study. Okay? So we'll start off with the simplest system. Okay? Now you'll be amazed that how many different systems this will apply to. Okay? So, and we'll see all of that. Okay? So, here's the restoring force. Mr. Hooke came up with this law, and it's known as Hooke's law. K is the spring constant. Okay? Stiffer the spring, bigger this number K will be. Okay? All right. So, what are we interested in? Here's the system. You stretch it and let go of that and let the system evolve. You want to know how the system will evolve. What you want to know is what will be the position of the mass as a function of time. Okay? All right, so let's derive the equation that will govern the behavior of this system. Okay? So the the algorithm is like this. You have a system. You put in a physics principle. That'll give you a mathematical model. And the mathematical model is generally a differential equation. Okay? And then you solve the differential equation, and there is the solution. So that's the recipe. Okay. So here's our system. Let's look at our system. Okay. Now this is a very simplified, system. What are the forces acting on this? Here's the force of the spring. Are there any other forces acting on it? Yes, there's the force of gravity, but we chose it like so because the normal force is canceling this. This force is canceling that, and there's no friction. So effectively, this is the only force acting on the system. Okay. So the force acting on the system is minus kx, and Newton's second law tells us that the net force, the force acting on the system, is equal to mass times the acceleration of the system. What is the acceleration? Acceleration is d square x by dt square. So the acceleration of this object is equal to minus k over m xt. Okay, what is k? That's the spring constant. That's a positive quantity. What is mass? Mass of the system, that's a positive quantity. So we know that k over m is positive. So just to make sure that there's no doubt about that, we'll call it omega squared, which is a positive quantity. And it turns out that that'll be related to the frequency of oscillation. What is the frequency of oscillation? If it oscillates 10 times a second, that's the frequency is 10. Okay. So we'll call that omega squared by times x. Okay. And then you bring it over here. Okay, so here is the equation, differential equation. So you've derived your first differential equation. So d square xt by dt square plus omega square xt equal to 0. What is this equation? Okay, what this equation is telling you is no matter what you do, you can hit this with a hammer. When this thing oscillates, the position of this guy as a function of time needs to satisfy this differential equation. Okay? That's what you came up with. And then you learn how to solve this differential equation. Okay? That'll give you all kinds of motion that this system can evolve into. Okay? That this system can execute. Okay? The solutions of this differential equation are the only solutions, only types of motion that the system can have. Okay? So you've completely solved this system. Okay. Did you guys understand that? All right. So you will learn how to solve these differential equations. A lot of it is trial and error, but when you take your differential equation class, they'll show you which trees to bark up at. Okay. Here's the solution. Okay. All right, so the two solutions that solve that differential equation are A cosine omega t plus phi and A sine omega t plus phi. Those are the only two solutions. Okay. So that mass that is oscillating, that's attached to the spring that's oscillating, has to obey one of those differential, one of these solutions. All right, let me point out a couple of things. So here's the differential equation. I'll write it again. D square xt by dt square plus omega square xt equal to 0. Omega square was k by m. All right, let's look at the solution. It doesn't matter which one. Okay, in this equation, what is this A? This A is not even showing up in the equation. What is this phi? That's not in the equation either. This omega is there in the equation. It's related to K and M, the spring constant and the mass. Okay. So this is a general feature. Okay. So now let me introduce some terminology. This is a second order equation. The highest derivative in this equation is a second order derivative. It's a second order linear differential equation. Linear meaning each term is linear. This is linear, this second order term is linear. This becomes an entirely very difficult problem to solve. Okay? This is not a linear equation. Okay? Forget that. This is very hard to solve. Okay? So this is a second order linear differential equation. Second order telling you that the highest derivative is second order. Okay, so when you have a second order differential equation, the solutions will have two constants that are determined by the initial conditions. Okay, so if this was a third order differential equation, linear equation, you'll have three constants. Okay, and the particular solution is determined by initial conditions, or they're also called boundary conditions. Okay, what would be the initial conditions? For instance, how far did you pull it, and then did you give it an initial velocity, or did you let it go with zero initial velocity? That's what these guys are related to. Okay, it turns out A will be the amplitude of oscillation, the maximum distance it starts off from, okay, or the maximum distance it goes to, and phi will be related to the initial velocity and all that. All right. So I'm going to pause here for a second and let you guys ask any questions if you have any questions. If not, I'll summarize what we've done so far. Okay, so here we go again. You will be interested in studying a system. Okay, it can be any system. So this is the simplest system we'll study. You want to study how the system evolves, meaning you want the configuration of the system as a function of time. This guy contains information. This describes how the system is evolving. Okay? All right, the evolution of the system is governed by an equation, okay, which generally is a differential equation. Okay? How do you come up with this differential equation? Well, you have to know the system and the properties of the system. You from the physics of the evolution, you get the mathematical model or the differential equation. Okay, system plus physics gives you the mathematical model, which is a differential equation, and then you solve it, and you have the evolution of the system. Okay? So that's what you're interested in. Okay. You guys understand? Okay. All right, so there is a solution, and once you have the solution, now you know you can calculate other things of interest. So you can calculate the velocity of the object as a function of time, and so you can calculate the velocity of the object as a function of time once you have the position, and you can calculate the acceleration of the object as a function of time. Okay. All right, so now, so there's the solution. Okay, x as a function of time is a cosine or a sine function. Okay, and this is illustrated physically here. So here's a mass attached to the spring. Okay, and you set it in oscillation, and you can simulate time by rolling this piece of paper at constant velocity. Okay. And if you attach a pen there, as this thing oscillates, it'll trace out a sine or cosine function. Okay. All right. Now, as this system is so here's our system. Here's the equilibrium position. what we'll do is we'll pull this mass to that position. That will be our amplitude, and then we'll let go of it, and what it'll do is it'll oscillate back and forth like that. Okay. How long will it oscillate?
Forever if there's no friction?
Yeah, forever if there's no friction. Okay. The time for one oscillation is called the period. Okay. And the period is given by this formula. So 2 pi square root of m divided by k. Okay, let's make sure that this makes sense. What would happen to the period if this mass gets heavier? The spring is the same. If the mass is heavier, what would happen to the period? It gets longer, okay? Because the pulling force is the same, and if you're pulling a heavier object, the acceleration is not as great, and the period will get longer. And that's what that's saying. If the mass is greater, the period will be higher. Okay? What if you have the same mass and apply a stronger spring? It'll pull harder, okay? And the period will get shorter. So, okay, higher spring constant gives you a shorter period. Frequency is inverse of period. Frequency tells you how many times it'll oscillate per second. Again, there's the frequency. Okay. Stiffer the spring, higher the frequency. Heavier the mass, lower the frequency. Okay. All right. So that's the main punchline of the chapter. Okay. So again, everything is summarized here in one sheet, this entire chapter. Okay. So I'll draw this again. Oops. Here's the system. Okay. We describe the configuration of the system by this coordinate. Okay, and that makes sense. This system was restricted to one-dimensional motion. Okay. And this coordinate of the mass, the position of the mass, described the configuration of the system. Okay. And the behavior of this system was described by this differential equation. You are experts at solving these kinds of differential equations, and there's the solution. Once you know the configuration of the system as a function of time, now you can calculate all things that are of interest to you. You can calculate the velocity of the system, the acceleration of the system, and so on. Okay? You're all done. Okay. All right, now I'll show you the amazing part. This differential equation, okay, here's why you study math. Okay. It turns out that this differential equation describes so many different systems. Okay. So you saw that it describes this system. Now, does this system look anything similar to this system? No, it does not. Okay? But it turns out that the behavior of this system is described exactly by the same differential equation that describes this system. Okay, so this is called a torsional pendulum. And if you twist this guy like so, it'll oscillate back and forth like that. Okay, just like this guy oscillates back and forth like this. Okay, so the configuration of this system, so here's the equilibrium position. The configuration of this system can be is most conveniently described by that angle, theta. Yeah? And we'll show you, I'll come to the slides in a second. That theta is described exactly by the same differential equation. So the behavior of this system is described exactly by that system. So here is a very different system, and if you are smart about the choice of describing the choice of coordinate to describe the configuration of the system, you get the exact same differential equation. How about this guy? Does that look any similar to any of those equations? No, not at all. And again, if this is the coordinate you choose to describe the configuration of this system, okay, that system will oscillate. This is called a simple pendulum, and you'll get exactly the same differential equation. D squared d theta and plus omega square theta t equal to 0, where omega square in this case is this constant g by L. Here's a different system. This is called a physical pendulum. And again, the behavior of this system is exactly again, so there is a coordinate, and the behavior of this system is also described by this differential equation. All right, so you see that how important that differential equation is, okay? It describes so many different, the behavior of so many different systems, okay? All right, so let's do some of the details. Yeah. Okay, again, so we started off with a very simple system, a mass attached to a spring. And this system oscillates because there's a restoring force if you disturb it from its equilibrium position. Okay? And right now we're considering systems where there's no dissipative forces. Okay? Meaning it's not killing the oscillations. Okay? And the behavior of the system was described by that differential equation. There's the solution. Okay? And there's the velocity, there's the acceleration. And the velocity is given by that. The maximum value of the velocity will be, when sine theta is 1. So the maximum velocity is omega a. Okay, so the magnitude of the maximum velocity is omega times a. Okay, the maximum value of the largest value of the position is when this is 1, and that would be a. So the physical meaning of a is the amplitude of oscillation. Okay, so the maximum distance this travels. And so you'll see if this system is horizontal, the maximum distance it'll go in this direction, it will also be a, and it oscillates back and forth between these 2 points. Okay? So a is the amplitude of oscillation. Omega is called the angular frequency. Okay, so a is the amplitude. Omega is the angular frequency. And omega is related to the linear frequency like so. And again, omega is related to the spring constant and the mass attached like that. All right, so here is the maximum velocity. And the maximum acceleration is given by, when this is 1, so it's given by a omega squared. A omega squared is the maximum acceleration. All right, now let me ask you this. You guys have done this in lab, okay? So I'll set this in oscillation. I'll pull this onto the side and let go, and it'll oscillate back and forth like that. When is the velocity maximum for the object? At x equal to 0. When it's at x equal to 0, that's when it's going the fastest. Okay, the velocity is negative when it's going in this direction, and it's positive when it's going in that direction. Okay? So velocity is negative. So when you let go at this point, it starts going faster and faster, and it's going fastest at this point. Then it slows down, stops, and then starts back again. It's going fastest at this point. When is the acceleration maximum? Okay, so let me give you a hint. Here's Newton's second law. When will the acceleration be maximum? when the force is maximum. When is the force maximum? This is the force only force acting on it. The force will be maximum when the position is the greatest from the equilibrium position. So at this point, the acceleration will be maximum. Okay. So when it's at its furthest point from the equilibrium position. Okay. So acceleration will be maximum here and there. Okay. So when it's going like that and turning around, the acceleration is in this direction. When it's here, the acceleration is in that direction. Okay. So at the extremities is when the acceleration is maximum. Okay. All right, now you pretty much know everything there is to know about this system. Okay. All right. Now at any given location, you can see. Let me go back to that. So you see, as this system is oscillating, this is a slightly more complicated system there because there is more gravitational potential energy as well. But you see the speed is changing. Okay, so let's try and apply that to our horizontal system. So as it's oscillating back and forth, its speed is changing. At any given location, there's the kinetic energy, 1/2 mv square, and we'll use this expression for the velocity, plug it in there, and there's 1/2 mv square. Okay. So that you can see that the velocity is a function of time. It depends on time. The potential energy is 1/2 kx square. We'll take this expression for x and put it there. Okay. So that is potential energy is a function of time as well. Yeah. And we saw that in here, even in this complicated system, you see the potential energy and kinetic energy are functions of time. Okay. But the thing is, if you add those two, well, here there's gravitational potential energy as well. If you add those two, the total energy is not a function of time, it's constant. Okay. And that's a general feature. So you add potential energy and kinetic energy, and the total energy is a constant. And when is that true? When is that true?
So you're not putting more energy into the system?
Or there's no dissipative forces. Okay. So for an isolated system where there are no non-conservative forces acting, the energy is constant. Okay. What does this formula give you? This gives you the velocity of the object as a function of position. Okay. This gave you velocity as a function of time. The position was a function of time, and these guys can be related. Cosine theta is 1 minus square root of 1 minus sine squared theta. So that's what's used there, and there's velocity as a function of position. When x equal to a, when it's at its extreme position, what is the velocity? 0. When x equal to a, the velocity is 0. Okay. Here's and this is equal to omega square, so that's omega is brought up. All right, so we already know that here are other systems that execute simple harmonic motion. Okay. So let's look at that. So this is called a torsional pendulum. Okay, when you twist this guy, this wire twists, and what it'll do is it'll bring the mass back. It'll make it oscillate. Okay, so it'll try and restore it. So you twist this, and it'll bring it back, bring the system back to its equilibrium position. Okay. Now, the stiffer the wire is, the bigger the torsion constant. The torsion constant is given by kappa. Okay. And so the restoring torque, in this case it's rotational motion, the restoring torque is minus kappa times theta. Stiffer the wire, bigger kappa will be the torsion constant. Okay. So for instance, if you have a cooked piece of noodle, what is the torsion constant of a cooked piece of noodle? I twist a cooked piece, 0. Right, very good. A steel wire will have a larger torsion constant. A tungsten wire will have an even larger torsion constant. Okay? Steel will have a larger torsion constant than aluminum. Okay? For steel, will a thicker wire have a greater torsion constant or a thinner wire? They're both steel. I'm sorry? The thicker wire will have a greater torsion constant. Okay? So, and so on. Okay? So that's the torsion constant. All right, so what does torque do? Of course, torques give you angular acceleration, so Newton's second law says, so torque is minus kappa theta, torque is I times alpha, so, okay, and alpha is d squared theta by dt squared. Okay, so there is your differential equation, and you can rearrange those terms, and you can get that differential equation. Okay, exactly the same differential equation for this guy. Okay, as for this guy, this guy's configuration was measured by that. Okay. This guy's configuration was measured by theta, where theta is that. Okay. So exactly the same differential equation applies. Okay. And then you can do all of that. Okay, omega is related to the torsion constant like that. I is the moment of inertia of this object about that axis. Okay. And the period is 2 pi m I over kappa. For the spring, mass attached to the spring, it was m over k. M got replaced by moment of inertia because this object was rotating about the axis. And k, the spring constant, got replaced by the torsion constant. You guys understanding this? Okay. I'm not going too fast, am I? All right. So now we saw that a very different looking system was governed by the same differential equation. Okay, so the model was modeled by the same differential equation. Okay, the evolution of that system was governed by the same differential equation. Here's a third system, a simple pendulum. Okay, and you set it in oscillation, it'll go back and forth. Okay, so here's the force of gravity. This component of the force of gravity is balancing the tension, and this component of gravity is is the restoring force. Okay, and that's what makes it go back and forth. Okay. So mg sine theta, the negative sign just telling you when theta is positive, that's the direction. Mg sine theta is equal to d square s. S is this distance, is mass times the acceleration. Okay, and again you can go through all of this. Okay, so as long as theta is less than 10 degrees, okay, for small angles, and you can test this, sine theta will equal theta. You can test this using your calculators, okay, and you have to convert that to radians. Theta is less than 10 degrees. You have to convert that to radians, which is less than 0.1 radian, okay, and you'll see that sine theta will approximately equal theta. Okay, so we'll replace that by theta, and then you get the same differential equation. So for small amplitude oscillations, okay, this guy behaves just like the mass attached to the spring. Okay. Again, so there's the solution. Theta max is the amplitude of oscillation. Okay. Omega is the angular frequency, and phi is again a constant related to the initial conditions. Okay. The period is 2 pi times L over G. L is the length of the simple pendulum. Okay. So a simple pendulum is any heavy object whose size is small compared to the length of the wire, the length of the string. Okay. Do you see any use for this guy?
Clocks?
Clocks, very good. So you can take an appropriate length and make the period 1 second. So there's 1 second. Okay. And so on. So this can be used for clocks. And again, in a system like this, the friction is very little, so it'll keep time steadily. And if there's a little friction and it dies, you just set it in a higher oscillation, and it'll keep working. Here's a physical pendulum. Okay. For a physical pendulum, now you can use anything. So you can use this guy. Okay. You nail it there, and when will it not oscillate? It doesn't oscillate when the center of gravity is right below the point of suspension. But you disturb it, and it'll oscillate. Okay. So any object can be used as a physical pendulum. Okay. So when the center of mass is right below the point of suspension, that's the equilibrium position, and you disturb it from that position, it'll oscillate back and forth like that. And here's the coordinate you want to use to describe the configuration of the system. Okay. And so when you disturb it, here's the force of gravity, there's the moment arm, the torque, the restoring torque is mg times d sine theta. Mg, the force, times the moment arm. Okay. And what does the torque do? It gives it angular acceleration. Okay. So mg d sine theta equal to I d square theta by dt squared. Okay. And for small angles, this can be approximated by theta. Okay. So mg theta small, mg d theta equal to I d square. Okay. And you can rearrange the terms, and you get the exact same differential equation. D square theta by dt square plus omega square theta equal to 0. Okay. Why would we be interested in this? Okay, again, you can calculate the period. The period works out to 2 pi I, the moment of inertia. The moment of inertia of this object about that axis. And mgd, m is the mass of the object. G, and what is d? D is the point of the distance from the of center of mass from the point of suspension. Okay. Okay, why would we be interested in something like this? Again, you can use this as your grandfather clock has a physical pendulum. Okay. But also here's an amazing fact. Okay, so when you walk, your leg is a physical pendulum. There is the point of suspension. How long did it take me to do one step? Half the period. So you can calculate the walking gait, the normal walking velocity for all angles. So That's a physical pendulum, okay? All right, so we studied 4 very different systems. Okay, so I'll summarize that again. Yeah. There was the configuration of the system. Here was the differential equation describing the behavior of the system. Omega square was equal to K, the spring constant, divided by mass. Okay. The configuration of this system was, there's the equilibrium position. The configuration of this system was measured by theta. Omega square was kappa, the torsion constant, and masses get replaced by moment of inertia. Okay? The moment of inertia of this object about that axis. What kind of system is this? It's a simple pendulum. What is a simple pendulum?
Is attached to
A tiny mass, tiny heavy mass attached to a long string. Yeah. So the dimension of this guy is negligible compared to the length of the string. Okay. So there's the length of the string. And again, that coordinate and omega square is equal to G over N. Yeah. So that was the third system, and the fourth system was a physical pendulum. And K and G. Okay. So you see 4 very different systems, and the evolution of these 4 systems is governed by the same differential equation. Okay? So you just have to be smart about the choice of the describing the configuration of the system, the coordinate you choose. Okay? So pay attention in your differential equation classes. Okay. Now we'll sort of switch gears. Well, no, we'll tell you a little more, a few more things about these systems. Okay. Now let's look at this guy. Okay, so here's uniform circular motion. Okay. What do we mean by uniform circular motions? An object that's going in a circle at constant speed. Okay. And you can do the following. You can use a lamp here and project the motion of this guy on this plane. Okay. It turns out that as this thing is going around the circle, the shadow of this guy is executing as oscillatory motion. Right? And this motion is exactly the same as this motion. You attach a mass and this oscillates back and forth. Okay, so the projection of a uniform circular motion in this plane is a simple harmonic motion. You can do the same thing and project the motion along this plane, and you get a simple harmonic motion in this plane. So, A uniform circular motion is a sum of two simple harmonic motions. Yep. All right. And the next few slides go over the proofs. By the way, we saw this in chapter 13. Okay, you guys remember that we illustrated this. Here's the International Space Station going around the Earth, and that motion is related to this motion if you dug a tunnel through the Earth. Okay, that motion is like a mass attached to a spring is related to the motion of the International Space Station. How long does it take for the International Space Station to go around the Earth? 90 minutes. And this oscillation would take 90 minutes. Okay. What this slide shows you is the following. If you're going around in a circle at constant speed, are you accelerating? Why are you accelerating? The speed is constant.
You're changing direction.
You're changing directions. The direction, okay. I'm sorry? Yeah, so, no, there's no tangential acceleration. There's centripetal acceleration. So you're going at you have an acceleration in this direction, and you take the component of this acceleration in this direction, that'll be exactly the same, that'll be the acceleration of this guy, of a mass attached. The acceleration of this guy is equal to that. You know, the velocity of this guy, so there's the velocity of the object that goes in a circle, uniform circular motion. This component is that velocity. Okay. All right, so those two slides, what they're showing you is that uniform circular motion and a simple harmonic motion are related. Uniform circular motion is two simple harmonic motions, the sum of two simple harmonic motions. Okay. All right, so what was the common theme here in these motions? What was absent? Friction was absent. Now in real world there is friction. Okay, so now let's try and handle the real world. Okay, it's a little more complicated. So there's an additional force. Okay. In these guys there was only a restoring force when you disturb the system, but now we'll add friction. Okay. All right, so here is a simple example. Okay. So here's your mass attached to the spring, and again, if it's moving in a fluid, there's friction. Okay. And the simplest friction we can model is the following. Friction, we'll call it drag force, is proportional to the velocity. What is this negative sign telling you? The friction force is opposite to the velocity. Okay, that's the simplest one to model, to solve. So you can't do this guy, you can't, all that gets complicated. Drag force proportional to acceleration is complicated, and so on. Okay, so this guy is easy to model, and he's also closer to reality. Okay, so that's what we'll model. And of course, if there's friction present, okay, the oscillations will die out. Okay. So if there's friction present, the oscillations will die out. Yep. Greater the friction, greater this value B is. Okay. So for instance, in this example, if you have this guy oscillating in a beaker of water versus a beaker of honey, in the honey, the friction will die out faster. Okay. Why would you want to study this? For instance, let's say Here's an example. Here's a wheel attached to this guy, which is essentially a spring. The shock absorber is a spring. Anytime you hit a pothole, you set it in oscillation, and you want those vibrations to die out fast. Okay. A wind can set a bridge in oscillation. You don't want that bridge oscillating forever. You want that oscillations to die out. Wind will set tall buildings in oscillations. You want to damp out those oscillations. Okay, so we are interested in that kind of stuff. All right, so there will be situations when you want to damp out oscillations. You want to kill the oscillations as fast as possible. Okay, so we want to study that. All right, you guys are experts at differential equations. Anytime you see a system, what is it that you set up? You set up a mathematical model. You set up the differential equation governing the behavior of that system, and then you solve the differential equation. Okay? What is it that you're interested in? You're interested in this guy. What is the position of that? What is the configuration? How does that system evolve? And that the configuration of that system is given by xt. Okay. All right. So again, you have a system. What is the algorithm? You have a system, physics. You input physics, mathematical model, which is generally a differential equation. All right. So let's do that. Here's Newton's second law. Newton's second law says mass times acceleration is equal to the net force acting on the object. Yeah. Now, it's not for this guy, but so this is for a horizontal object, a horizontal mass attached to a spring. There is kx, and if the velocity is in that direction, the drag force is in this direction. Okay, so the net force is the force on the spring constant, and there is the drag force. Okay, greater the friction, greater B will be. Okay. Acceleration is d square x by dt square, kx, and velocity is dx by dt. Okay. You rearrange all those terms and we'll bring it over here. Okay, now I'll do this. So d square x by dt square plus b over m dx by dt plus k over m xt equal to 0. This was omega square. D square x by dt square Okay, so your frictionless system was B equal to 0. You get back your frictionless system, it turns out to be a special case of this equation, for B equal to 0. So with friction, you got this additional term in this differential equation. Again, so this is a little more complicated to solve, but you guys are experts, and here's your solution. Okay, so it looks like exactly the same equation, except that there's an exponentially decaying term, and which depends on the friction coefficient. Greater the friction coefficient, faster this term dies. So the amplitude is dying exponentially. Okay, so it's exactly the same. See, it's oscillating, except that the amplitude is dying exponentially. Okay, here's another thing. The frequency of oscillation, see that there was the frequency of oscillation without friction. The frequency of oscillation is decreased slightly. And that makes sense. With friction present, it's going to take longer to oscillate. And it's not going to oscillate as many times per unit time. Okay, so the frequency decreases as well. All right, so there you go. Now you solved a real world problem, okay, with friction. Yeah. Now let's look at this equation. So the frequency is decreased. What if you put enough friction such that this term is equal to that? This becomes zero. Frequency becomes zero, meaning it's not going to oscillate. Okay? And you want that in many situations. Again, let's say you hit a pothole with your motorbike. It extends. You want to kill the oscillations as fast as possible. Okay? So when this is zero, that's called critically damped system. Okay? All right. So here it is oscillating. When B is such that it doesn't oscillate, that is critically damped. When B is such that this term is zero, that's critically damped. When B is bigger than critical damping, the system won't even come back to its equilibrium position. Yeah. That's overdamped. When this term is greater than that, that's an overdamped system. And you don't want that either. Okay? So you want critically damped or just under critically damped system in your real world situations. Okay? What do you think this is?
When you put an external force.
I'm sorry?
When you apply an external force
Right.
on an oscillations,
Right.
because there is damping.
Very good. Very good. So if in a system you want to keep the oscillations going, okay, then you want to apply, if there is friction present, friction is bleeding energy, and so you want to put in energy. Okay? You guys know of any system like this?
A record player?
A child on a swing. You know, as the swing oscillation dies, what happens? The child cries, and so you want to keep pushing that system, right? There are many systems. Okay, so in a motor, you keep adding power because otherwise the motor would stop turning. Okay, how much power energy are you adding every second? If a motor is rotating at a constant rate, you're adding as much energy as is being converted into friction, as is being lost. Okay. So forced oscillations. Okay, so per cycle, if you're putting in as much energy as is being lost, then you'll maintain that oscillation. If you're putting less energy, then the oscillation will die. And if you're putting more energy, then the the amplitude would increase. Okay, but there are conditions to that. Okay, so there are situations. All right, so this is an extremely important thing, and make sure you understand this. So forced oscillation, again, it's possible to compensate for loss of energy in a damped system by applying an external force. Okay. The amplitude of motion will remain constant if energy input per cycle exactly equals the decrease in energy per cycle. All right, so again, what have you learned today? You have a system, the first thing you're going to do is come up with a mathematical model for the system. Okay? So we'll start off with Newton's second law. Okay, there's the spring force, there's the friction, and here's the applied force. Okay, so what we're going to do is when you're pushing the child in a periodic manner. So we're going to apply a periodic force. Okay. Here's the amplitude of the force you're going to apply. Here's the fact that it's periodic. Okay. And what this term says is the driving frequency. This is the driving frequency, the frequency with which you're going to apply the force. Okay? And so there's the net force acting on the system. That should equal mass times the acceleration of the system. So you got your differential equation that easily. Okay. All right, so there's the differential equation. And again, this is a little more complicated to solve. Okay, so the solution has this form. The amplitude depends on the driving frequency and the natural frequency of the oscillation. What was omega? Remember, omega was k by m minus b by 2m squared. Okay. So that was the natural frequency. So the amplitude depends on that, and the system will oscillate at the driving frequency, the driven frequency. Okay. All right, what is this graph telling you? So this is what I want you to understand. Okay, this is the scary part. We've talked about resonance before. Look at this. So the amplitude, we're plotting this function, the amplitude of oscillation, as a function of the driving frequency. Okay. So as driving frequency increases, okay, we're plotting this ratio, we're changing the driving frequency. Look at that. When the driving frequency is 60% the natural frequency, the amplitude is small. As the driving frequency equals a natural frequency, this amplitude gets tremendously large. Now, we'll be interested. Okay, so when the driving frequency matches a natural frequency, you set up large amplitude oscillations. Okay. I will show you a simulation of that. I'll show you a video related to that. This is called resonance. What is happening is you're supplying energy at the right time. If you push the child at the right time, you can set up large amplitude oscillations. Okay. So let me show you a simulation. Yeah. So again, here's the amplitude. This function, again, like I said, it's a complicated solutions. It's related to the amplitude of the driving force, the mass, and here's the driving frequency and the natural frequency. See, when the driving frequency matches the natural frequency, this term goes to 0 and A takes its maximum value. And if the damping is low, lower the damping, higher the amplitude. All right, so let me show you a system. Okay, so here is what we're going to simulate. Here's your mass attached to the spring. That's your system, and we are going to hold on to the spring and pump energy in, and we're going to drive that. Okay. So here's the first case. The driving frequency is not close to the natural frequency. Okay, so we'll so here is the driving frequency, and so we'll start this. Okay, so you see we're driving it, except that frequency doesn't match the natural frequency, and you're not pumping energy at the right time. Okay. Now, Okay, so now what did I do? I made the driving frequency close to the natural frequency of oscillation. Okay, so now I'm going to drive the system at a frequency matching the natural frequency. Okay, and watch what happens. You see the driving amplitude is the same, except that you're pumping energy in at the same time, at the same frequency as the natural frequency of oscillation. And you can set up large amplitude oscillations. Imagine that was the wind and this was a bridge. You would collapse a bridge. Imagine that was an earthquake and that was a building. If the frequency of the earthquake matched the natural frequency of a building, it would collapse. The frequency of a building is, natural frequency of a building is strongly related to its height. Okay. So let me show you a little app. I'm sure you guys have seen this. So this was a bridge built in the 40s near Seattle. Walking along what is called a node. A node is a point, in this case a node is a line which doesn't vibrate. We'll do an experiment next semester with a string. didn't last not even a year. Okay, so what is the solution to that? Okay, so you don't want the amplitude to get too large. Okay, so random forces in nature, their frequency, if the driving frequency matches a natural frequency, you can set up large amplitude oscillations. Okay. Well, how do you minimize this amplitude, the maximum amplitude? You see, if B gets bigger, if damping increases, then you can limit the maximum amplitude of oscillation. So you have to place dampers in structures. All bridges have them. And this is an old problem, and it's not easy to figure out. So this Millennium Bridge in London was, this bridge was built in 2010 or whatever. You can read the Wikipedia page. The first day, 3,000 people walked on it, and it set up oscillations. This was a $15 million bridge. They had to close it the first day. They spent $5 million putting dampers, increasing that beat. Okay, so this kind of stuff is hard to calculate. And anyway, read that Millennium Bridge. Okay, so again, in all structures, you want enough damping to make sure that your amplitude of oscillation doesn't get too large. Okay, so the increase in amplitude is called resonance. So when do you have resonance? When the driving frequency matches the natural frequency of oscillation, okay, you get resonance. And you can set up large amplitude oscillations. Okay. Okay, so it turns out that the natural frequency of an oscillation of a building is strongly related to the height. Okay, and an earthquake happened, and it's shaking the ground, and that's the driving frequency. This frequency happened to match the frequency of this building, and this guy collapsed. This frequency doesn't match the frequency of this guy, and those guys survive. All right, so in tall buildings, you have this building can sway up to 2 meters at the very top. 2 meters is almost half that table. That's the most expensive floor. And you want to pay that money if you get dizzy. So here's a damper. Okay, so here's a tall building. There's a large water tank containing 300 gallons of water. So when the building sways this way, the water will just stay back that way, and it goes out of phase, and that'll damp the oscillation. Okay, so what is that guy doing? That guy is increasing B. Okay. So you have to have dampers in buildings. Okay. So there is the damper in the Type A tower. So there is the Type A tower, and at the very top these are dampers. So as the building sways, these will that's a heavy mass there, that will dampen the oscillations. All right, so resonance is a scary phenomenon, and it can compromise your structures, and you want to make sure that doesn't happen. So if you're a civil engineer, if you want to be a civil engineer, you have to be aware of all of this.